Continuing on this theme, we're now going to look at two approaches to the persistent threat of wildfire, another topic that's come up for a number of times already this morning. From nanoscale to wildfire plumes, effects of wildfire smoke on climate change. Please welcome Michele Barbato, Director of CITRIS Climate and Professor at UC Davis, who will moderate this conversation. Michele.
Hello. I don't know if my video can start. But I hope everybody can hear me. It is my pleasure today to introduce and to moderate these two approaches panel on the effects of wildfire smoke on climate change. Today, we have two distinguished scientists, Dr. Allison Aiken and Dr. Hsiang-He, who are investigating the effect of wildfire smoke on climate change from two very different, almost opposite perspectives. On one side, the investigation at the microscopic molecular scale of what different chemical species are doing in terms of effect on climate change. And then on the other opposite, at the very large scale of hundreds of miles, corresponding to the fire plumes coming from wildfires. So our first panelist is Dr. Allison Aiken from the Los Alamos National Lab. Allison has a PhD in chemistry from the University of Colorado at Boulder. She has been at the Los Alamos National Lab since 2010. She's a former director, so postdoctoral fellow. Dr. Aiken is an analytical and atmospheric chemist focused on the experimental and observational aerosol science with extensive experience in conducting experiments in the lab and in remote field locations. And so with that, I'd like to introduce Dr. Allison Aiken.
Thank you, Michele, so much for that great introduction and the opportunity to speak to everyone today. I'm excited to be talking about how wildfires are important and affect human health and climate as well. They are the largest source of carbon emitted to the atmosphere globally. And the carbon being emitted is both in the gas phase and the particulate phase, which is why we study both at Los Alamos. The larger and hotter fires are also predicted to occur as the climate warms in the future, which is, of course, very relevant to California and the Southwest United States in general, as we've already been seeing increased fires over the last few years. Recently, it's also been implicated that wildfire emissions may even be more toxic to humans than urban emission sources. So based on that, we speculate even further that the wildfire emissions at wildfire-urban interface may have even higher toxicity due to the burning of man-made materials that was mentioned in the previous session, instead of just natural woods and plant materials. For this reason, we've been studying emissions from building materials. And some of these compounds that are emitted are known to impact human health, specifically like formaldehyde and polycyclic aromatic hydrocarbons. We can study these during wildfire events and also laboratory biomass burning studies. In our lab experiments, we've already seen in preliminary data that it looks like more formaldehyde is being emitted from the man-made construction materials than from natural woods. The small particles that are being emitted can also impact the climate depending upon their physical properties, optical properties, and chemistry. Black carbon can warm the atmosphere, while inorganics and organics can cool the planet. We're very interested in these particles that are emitted from urban and natural sources due to their effects on both human health and climate, as I mentioned in the beginning. So we've been studying these gases and particles that are being emitted under different burning conditions from different fuel types to understand their impacts on climate. We can do this by studying wildfire plumes in the atmosphere, but we can also burn different fuel types in our lab as well. To do this, we use high time resolution online instrumentation that, for the most part, are large and bulky, unlike the smaller, newer devices that Suzanne was talking about. So we use Examples like aerosol mass spectrometry, single particle soot photometry, photoacoustic soot spectroscopy, and scanning mobility particle sizing. Lately, we've been studying black carbon a lot, as it's very important since it directly warms the planet by absorbing solar radiation. The amount of warming per mass of black carbon can also increase when other compounds condense onto the black carbon cores, focusing that absorption onto the core of the particle. So we've been studying how these coatings impact the absorption from black carbon, both in the lab and in the field. We have also observed that there's more black carbon that is emitted during hotter fires in the laboratory. Optical properties reflect this as well, showing more absorption and lower single scattering albedo for those experiments. The size of the particles emitted from biomass burning experiments is largely variable and highly dependent upon the environmental conditions. And so that requires more research as well. In addition to the black carbon, there's of course other components being emitted, inorganics and other organics. Suzanne also talked about a little bit about brown carbon and tar balls. Those particles have been less well studied in terms of their absorption properties, but they are also highly absorbing in the visible region. From our experiments, we see more of them produced from the lower temperature burning experiments. All of these particles can have different impacts too, depending upon where they are emitted in the atmosphere. For example, you can have large pyrocumulonimbus that form and inject particles directly into the stratosphere, where they can be transported around the globe. Depending upon the atmospheric conditions, they can be transported back to the surface too, potentially impacting human health far from the source, as well as climate. This is another example of how wildfires have not only regional impacts, but can impact the larger Earth system and humans all over the globe. So once again, we are all in this together. In addition to the direct warming of the atmosphere, many particles can also alter cloud formation and rain patterns, impacting the hydrological cycle. These are some of the many reasons why we are studying aerosol chemistry, physical and optical properties, and water uptake, both in the lab and the field. We use our controlled burning experiments in the lab to better understand the complexities we observe in the atmosphere. As the plumes are evolving chemically in time in the atmosphere, the particles can have very different properties and very different properties than they had at the source of where they were emitted initially. Our goals are to better understand the key properties and processes that are important for understanding the role of wildfire emissions on climate and human health. And to do so, we're using key instrumentation to understand the chemical and optical properties of these particles, in addition to monitoring the gas phase emissions as well.
I guess it comes back to me. Much, Allison. That was a lot of material in a very short time. It's a big topic that we are treating here. I'm very curious to hear now the other aspect of the problem from our other panelists. Dr. Hsiang-He from the Lawrence Livermore National Lab. Dr. Lee is an experienced research scientist with a demonstrated history of working in the research industry. She currently works at the Lawrence Livermore National Lab. She has a PhD in atmospheric science and meteorology from UC Davis, from our campus. Dr. Lee's research interests include wildfires, regional air quality, and the application of machine learning on wildfire and climate studies. And so without further ado, please, Hsiang-He, let us know more about this problem of wildfires and climate change.
Thank you, Michael, for the introductions. And it's my honor to be invited to the symposium. And I guess that most of the audience are living in California or west coast of the United States. If so, you definitely experienced the bad air quality in the recent years. And if you have been living here more than 5 years, you may even notice that the wildfire occurred more frequently and on a large scale. You are correct. And based on the government report and the research study, in the recent years, the extreme wildfire have more frequently occurred in the Western United States, even Canada, And we know the immediate impact of the wildfire is loss of the household properties and the human life. And however, the abundant the aerosols, the smoke particles, and that's what we call the aerosols, and the emitted from such fire and can cause the haze event in the downwind sides and degrading the visibilities and threatens the human health. And we heard a lot of the cases in the previous sections. And the low visibility can slow down the economic activities like aircraft departure and landing and outdoor activities shutdowns. And the smoke particles like PM2.5 are from the fire smoke and affect the heart and the lungs, especially in people who already have the chronic heart or lung disease. And I remember the first month I was on board in the Livermore National Lab. That was November 2018. The campus was closed due to the unhealthy air quality. So besides the causing air quality issues, the smoke particles from the fires that can affect the cloud formation and the convection systems, and those that can change the rainfall pattern. I have the one research papers that are discussing the impact of the wildfire particles that effect on the convections there in Southeast Asia. And there's certain wildfire have stronger diurnal cycle and could affect by the orographic. Once the wildfire perturb this type of rainfall, it could delay the rainfall and change the rainfall location. You can think a lot, most of the wildfire regions are already quite dry. And the delayed rainfall means it's supposed to rain in the fire region, but the rainfall moves to the downwind side and it could make the fire region even drier. And the chemical components of the smoke particle can reduce the sunlight through the absorption and their scattering. It even changed the radiation project. Do you still remember in September 2020, just at the beginning of the pandemic, the sky turns orange in the Bay Area and the people just think, oh, wow, that's kind of so unreal. And people feel like living on Mars. That's why we started the wildfire and the wild smoke, because those smoke particles and either thermal heat release from the wildfire can change regional temperature, rainfall patterns, and cause extreme weather systems. And mentioning about the extreme weather system, I would like to introduce one term. It's not really common, called pyrocumulus. Pyrocumulus are fire-triggered thunderstorms that can transport large amounts of smoke particles to the higher altitudes, which we call the lower stratosphere. And then there is about 12 kilometers or 7 miles in altitude. Why we care about the pyrocumulus systems or pyrocumulus events? Because the pyrocumulus or volcanic eruptions are important geophysical extreme events. They can perturb the stratosphere, the aerosol loading, and have a substantial climate impact locally and globally. Give you a rough idea about aerosol lifetime in the troposphere is about 7 to 10 days. But once the fire particles and inject into the lower stratosphere, they can stay in the air for several weeks or 2 months. So those small particles inject into the stratosphere from the pyrocumulus, meaning contain the black carbon and the organic carbons, and which have the quite different radiative effect from the sulfate aerosol released from the volcanic eruption. Volcanic sulfate particles have a stronger cooling effect due to the scattering. But the carbonaceous particle, especially black carbon, reduce the sunlight through the absorption and the scattering, leading to the atmospheric warming and the surface cooling. It would completely change the temperature profile. In the previous studies, some research concluded that the heating from the black carbon shortwave absorptions, giving the rise of vertical motion and light that can carry smoke above the original injection height around the tropopoles. That means that they can transport to the higher altitude. Though the radiative effect of those pyrocumulus that inject smokes in the stratosphere can be very important in the global radiation budget. That's why the research focus in our lab gradually shifted from the troposphere to the stratosphere, because the impact of the fire aerosols in the stratosphere can be larger and broader. So I would like to give back to Michael.
Thank you. So this is all very interesting. It seems like one of the common elements between Allison and Hsiang-He research is the prevalence of black carbon and how much black carbon we have in wildfires, and then how it affects the aerosol radiative properties. So let me ask one question each. What is the fraction of black carbon that we generally have in lab experiments? And that is a question for Allison. We can make it all in these 4 minutes. Hsiang-He, can you explain also how that translates in terms of the radiative properties and the effect of stratospheric aerosol on climate change? So Allison.
Yes, thank you for that great question. So we have been conducting burns at different temperatures from 600 degrees Celsius to 1,000. And the burns that are done at the lower temperature, around the 600 degrees Celsius, all seem to emit between 1% and 2% mass fraction of black carbon. Whereas the hotter temperature burns at 1,000 degrees Celsius, we've seen anywhere up to 10% black carbon mass fraction.
And that's actually a temperature that our wildfires are starting to reach, because the mega fires are burning around that temperature, or even a little bit higher than that. So that's a lot of black carbon.
Yes.
Hsiang-He, so can you comment on what is the effect of that on the global warming?
Yes, so people actually start thinking about inject the small particles into the stratosphere, kind of geoengineering studies that can slow down the global warming. But somehow actually it's more complicated than we thought. And because the particles component different, like we inject the sulfate or inject like the different like the carbonaceous particles, that they could have a different climate impact globally. And so it's not a kind of easy thing. Okay, we are sending out a bunch of the particles in the air, and we can slow down or cooling down the surface. Actually, you also have a certain chemical reactions that will come with the other ozone or certain even greenhouse gases. So that's why geoengineering studies have to slow down and have to be more cautious. And we have those nature disaster like the Dome Guard or the volcanic eruptions that are just happening in the previous few months ago. And those are kind of quite cool experiments, the nature experiments, to see how the global feedback for those kind of events.
Yeah. Thank you, Hsiang-He. I think we are eating our time, so I'm going to wrap up. Thank you very much, Dr. Lee and Dr. Aiken, for their very interesting presentations. Again, thank you everybody also for attending, and I hope it was interesting for everybody to hear what is going on in research and what research can do and how it affects our world in terms of climate change. And I'll give it back to Camille.
Perfect. Thank you, Michele. We really appreciate you and Dr. Aiken and Dr. Lee for your conversation. Really enlightening. Many of us recall the reddened skies and the really poor air quality due to the 2021 wildfires and those before that. So thank you for enlightening us on the scope of the issue and the research that's being undertaken to address it.